Thanks a lot, Bastien, for the invitation and the very nice introduction. Hi to everyone. I'm very happy to be here to talk about compound weather and climate events. I am leading the group on compound climate extremes at UFZ Leipzig, and this is a group funded by the Emanuele program, the DFG one. And here today I'm talking about work developed by myself and group members largely. And yeah, let me start introducing what compound events are, although I assume by now many of you may be aware of the topic itself. And to do that, it's worth referring first to traditional assessment, which have generally focused, especially until the recent past, to univariate extremes. So you can think of temperature extremes or precipitation extremes, and these are relevant events because they can cause heat waves and floods. However, the reality is that most of the climate-related impacts are actually caused by compound weather and climate events. So these were defined as a combination of multiple climate drivers and/or hazards that contribute to societal or environmental risk. And on this graphic here on the left, these drivers and/or hazards are simply encapsulated into variables, which somehow contribute to some impact variable as well. As a simple example of these events, you can think of a crop failure, which in some areas can be favored by high temperature and the lack of rainfall. And all of these drivers and/or hazards that we have can actually combine in many different ways so as to result in many different compound event types. And this is why actually we try to categorize them in a, let's say, synthetic way into three main types, which are multivariate, temporally compounding, and spatially compounding events. And what I want to do now is to provide an example for each of these types, and then some, let's say, more potentially complicated events that combine features of the different types as well. To start with multivariate events, these are events that occur when multiple drivers, let's say hazards, combine in the same location so as to enhance some sort of impacts. And the most popular event, one of the most popular events in this context are compound coastal flooding, which arise in low-lying coastal area when there is heavy rainfall and at the same time a storm surge pushing the waters towards the coast and therefore obstructing the water of the rainfall from draining into the sea, therefore leading to a flooding. Here it's shown in this video the water coming inland from the sea due to a storm surge, and at the same time in this location there was around the same time a large amount of rainfall, and the two drivers together led then to this compound coastal flooding in this area in Calabria in Italy. Temporally compounding events instead are events that occur when multiple drivers and/or hazards affect a region, and this overall can lead to some impacts. This is an example of an event which was not highly impactful, but it's just that I experienced this myself, so I put it here. It happened in Reading in 2020 when I was living there, where there were three storms, actually, as you can see here from this time series, that hit the region of Reading, one after the other. In Reading, this led to moderate or rainfall only, but the fact that they happened one after the other, together with the moisture that was already available in the soil, led to this flooding there. It was a minor one, but of course, events like this can also lead to much more extreme and impactful results. And finally, we have the spatially compounding events, which happen when multiple events in different areas of a large region or even of the world happen, and somehow they combine so as to lead to some impacts or to affect some integrated system. In this case, the integrated system in the example is the food security one. And the example is about the ENSO-driven synchronous crop failures that happened in 1983. So we see here the anomalies in the maize production across breadbasket regions. Basically, there were droughts across the key breadbasket region in the same year, and this led to little production in each of these in many of these regions. And altogether, this reduced the global scale, globally aggregated crop production. And events like this can clearly challenge the food security because such a global little production may, for example, threaten poorer countries, for example, that can have difficulties in importing crop, for example. And this, by the way, was one of the three strongest El Nino in the last 150 years. Now, as another events where we can start to see different features of compound events playing at the same time, we have the drought that happened in 2022 in Europe. You can see here the soil moisture simulated by an hydrological model, which shows that the dryness was very widespread across multiple countries. From the images on the right, we see from the satellite UK and France, very dry, and then the north of Italy through the Po River, which was also very dry. Indeed, the event actually transitioned to an hydrological drought in many areas. And there were impacts of different type, but the event was driven by a combination of effects. There were this hot, dry weather. There was this hot, dry weather across multiple seasons. So we have multiple variables across multiple, let's say, time steps. And this is what led to this very extreme drought. And there were impacts such as a limited municipal water supply, especially I remember in the northern part of Italy and in France, for example, reduced crop yield, also decreased hydropower generation, which led to the shutting down of some hydropower plants, and also navigation restriction in rivers such as the Rhine, because of of course, low water, which led to issue with transporting food, for example. Another type of event is the one that happened in 2025, when we can also see some compounding feature. This is the map of the fires on August 15th, this last summer. And you can see that there were fires across multiple regions at the same time. Unfortunately, this event was very extreme to a point that also led to victims in Spain, and was very extreme at a continental scale, as shown by the fact that the European aggregated burnt area was the largest value for a calendar year in August 2025. Now, events like these can challenge the European civil protection mechanism, which is there basically to share resources to cope with fires when this fire occur. So if a given country is under a large fire, it can request help from other countries. But of course, if you think of a situation where multiple fires happen at the same time across multiple countries, these resources at some point can become overwhelmed, and this can affect the impacts that can, in principle, escalate. This is what was reported. I mean, the European protection mechanism highlighted that in 2025, there were these fires occurring at over multiple regions, which challenged the response. And so this is an example of a specially compounding event, an event that is driven at the same time at each location by a combination of hot, dry, and windy conditions. Now, given that many impacts are actually caused by compound events, I've shown just some example here. The key aspect here is that it's relevant to take a compound event perspective on weather-related extremes, because this can allow for a better understanding of the drivers of the events, as well as of the climate change influences. And this is actually what we do in my group. Yeah, there are a couple of papers I won't have time to dig further into, but if you are interested in, you can give a look. The second one, for example, provides some guidance on how to study these different types of compound events that were defined in the first paper on top instead. What I would like to do now is to provide some conceptual inputs that I think are relevant to study compound events, and then slowly transition to some specific case studies. As a first step, which are the statistical ingredients of compound events? You can think of two variables, x and y, which are those you're interested in because they can cause some impacts. For example, precipitation and sea level can favor coastal flooding, as we have seen, or high temperature and low relative humidity can lead to fire risk. So you can be interested in the distribution, therefore, of these two drivers, x and y, because you may want to know what's the probability of having concurrent extremeness in the two variables. And here, what I want to bring up as a concept is that this PDF can be obtained as the product, actually, of the marginal distribution of the two variables. So the marginal distribution of x is the distribution of x regardless of the other variable, and the distribution of y, and then a third term, which is the dependence between the variables. So this is called the copula density. Now, we don't need to go into mathematical details here, but There is even a very elegant theorem that indeed allow us to write such a PDF as the product of these three terms. And this applies to any dimension, basically. So the key message here is that there is a dependence, a statistical correlation between the variables that has to be taken into account. And that's because this correlation matters. For example, if we look at a system where we have two variables x and y, they can be independent as shown here, and we may want to know what's the probability of concurrent extremes of the two variables, which here is our compound event by definition. Well, such a probability can be enhanced by if the variables are dependent. And this is something that happens in reality. For example, it has been shown for the case of concurrent hot and dry summer based on real data. This is the ratio of the probability of concurrent hot and dry summer as observed to the probability that one expects if the variables temperature and precipitation were independent. A ratio of about 6 in some regions highlights that this dependency can enhance the probability of occurrence of these concurrent extremes. And this can be related to physical mechanism. In this case, it's a matter of large-scale atmospheric circulation. So when it's good weather, there is no rain and radiation that can lead to high temperature, but also then the atmosphere feedback through modulation of sensible and latent heat fluxes. And this is something that you can also find in other systems, of course, such as storminess leading to compound coastal flooding. The fact that there are dependencies and across variables, but also the marginal distribution to take into account means that if we look at changes in the probability of compound events, defined again as concurrent extreme in two variables, you need to account for the fact that the dependency between the two variables can change, and then simply the distribution of each of them, as shown here in this case for one variable, can change. This can be seen in practice. Here we looked, for example, at changes in the probability of concurrent precipitation and storm surge extremes in the future, with a map showing in red that this probability is increasing over Northern Europe, and it tends to decrease actually over Southern Europe. We could ask here, what's the contribution to these changes arising from precipitation changes, which is shown here, from storm surge changes, which is shown here, and these two actually align with our understanding of the changes in storminess and the thermodynamic processes. And then we could also ask what's the effect of changes in correlation between temperature, between precipitation and storm surges. Here we got a lot of gray, which means uncertainty across climate models. Basically, here the sample size of the models was too small to robustly disentangle changes in the dependency, changes that might be anyway also small in this case. And these highlights bring me in another related topic, which is the topic of the sample size, which has to be large for robustly studying compound events. This is illustrated here in a very simple schematic where you have two drivers and their distribution and the compound events, which are basically rare events by definition because they are in a corner of the multivariate space. Therefore, you need a large sample size to sample them, and such a large sample size can also allow to identify more extreme compound events. In this context, SMILES, which are single model initial conditions large ensemble, can help to study these compound events in the model world. A SMILE is basically a climate model which is run multiple times starting from slightly different initial condition, and this leads to multiple equally valid realization of the climate system or ensemble members, or let's say realization for the given variable we are interested in. And one can put all these members all together basically to derive a large sample size that enable studying compound events in a robust way, especially when we are interested into probabilistic assessment in the model world. The fact that a large sample size can allow to identify compound events is also shown by this illustration, where we looked at compound wind and precipitation extremes over Portugal, which can cause, for example, coastal flooding or enhance landslide risk. We looked at the most extreme event in a compound event sense when using for one single ensemble from a climate model, and we got this extreme event, or when we used all available ensemble members from a climate model, and we got this event. Now we can see that actually the event that is really compound is the orange one. Indeed, if we look at a map of this day that is captured by this point here on the scatter plot, we can see that this is associated with a low pressure system and associated wind extremes as shown by the green stippling. Instead, if you look at the other events, the low pressure system is much deeper and it is associated over Portugal with concurrent precipitation and wind extremes. So a large sample size can increase the probability of identifying basically compound events in your dataset, which is in line with the curse of dimensionality as a concept. The fact that we need a large sample size to study compound events implies also that estimates based on small sample size can be misleading. This is about estimates of probability, or let's say frequency of compound events. And this is shown in this illustration for frequency of hot dry summer, which was derived here based on hundreds of years of data from a climate model. And as an illustration here, we could see that if we had quantified, let's say, if we quantify the same frequency, but based on a single ensemble member only, so 31 years of data, we could identify both a very low probability of hot dry events or a very high one. So by chance, if we had used a small sample size, we could have indicated the low risk of compound events in Europe here, which is a region that in reality we can see here on the left is at high risk, or let's say has a high probability of compound hot dry summers. And of course, this has an implication of also for observation-based estimate that we should be aware when are based on a small sample size can be highly uncertain, and therefore this provides indication on how to interpret observation-based results when based on small sample sizes. Yeah, it's also worth mentioning that such uncertainty that I've mentioned becomes larger when the dimensionality of the compound events increase. Think, for example, about probability of concurrent droughts across multiple breadbasket regions, and also when the dependency across the drivers, in this case of the example precipitation and temperature, become small. As a last concept I want to highlight here, which relates also to the talk of Wilson Jan of the last or 1 or 2 weeks ago, is that storylines can help for communicating uncertainties in projections. When we look at future climate, there starts to be uncertainty from model difference that can be very large. And here we are showing that the probability of hot, dry summers over the Amazon according to 2 different models can be very different, as shown here by these 2 different maps. We could end up with a dry storyline with high frequency or wet storyline with low frequency. And these storylines can enable to basically communicate in a transparent way this uncertainty, going beyond the multimodal mean, which sometimes can be very misleading as it hides the fact that there are some models showing the potential for some bad or potentially bad worst case scenarios. Okay, with that, I am moving now to some more, let's say, specific case studies. And the first of them relates to the drought of 2022 that I have already introduced earlier on. Just to add to what I said before, on this map showing the dryness over Europe, you can also, for soil moisture, which by the way was obtained through MHA methodological simulation for Swifthope's weather data, you can also see on the map, as I was saying, some magenta stippling. These are locations where 2022 was the driest simulated summer of the last 60 years. So it was a very extreme summer. And this extremeness can also be visualized by looking at the European total water anomaly, showing that 2022 was the driest summer, but also at a special extent of the drought across the domain. This event, through factorial simulation, we could demonstrate was driven, as I anticipated earlier, by compound hot, dry weather across multiple seasons. And what I'm focusing on here only is what was the contribution of human-induced climate change on the drought. And to do that, we take a storyline approach. meaning that basically we simulate soil moisture first under observed temperature and precipitation, and then under counterfactual precipitation and temperature. Then we compare the two, and we can look at the climate change effect. And just as a note here, as a relevant note here, the way the counterfactual precipitation and temperature are derived is the following. We remove the CMIP6 base change of seasonal mean temperature and precipitation from the observed daily time series of these variables. By doing that, we can derive the climate change contribution across the domain, which is basically this map is telling that climate change dried out the soil virtually everywhere over Europe. There are also some magenta stippling you can see on this map. These are locations where the summer of 2022 would have not been the driest simulated in the last 60 years by the model if we had not taken into account human-induced climate change, highlighting, therefore, how climate change really led to very extreme conditions. To this counterfactual data we produce, we could also look at the effect of temperature only, which led to basically drying the soil everywhere in Europe due to higher evaporation, and then at the effect of precipitation, which led to wettening and drying the soil over northern and southern Europe, respectively. We can take then a more continental scale perspective and look at the amount of water, the anomaly in the soil moisture we had in the summer of 2022, according to the simulation, and the lack of water due to climate change. Comparing the two, we concluded that human-induced climate change caused about 30% of the total European deficit, which was largely driven at this continental scale by temperature, due to the fact that the effect of precipitation, which is heterogeneous in space and also very uncertain, cancel out at this continental scale. Here we also asked another question, which relates to the fact that we do know that human-induced warming was there well before of the hydrological year of 2022. So in principle, such a warming may have started to dry out the soil before the hydrological year of 2022, and therefore ultimately contributing to the dryness in the summer of 2022. So we estimated this effect, and we concluded that about 40% of the climate change contribution was actually mediated by the warming before the hydrological year of 2022, which we refer to this as a lagged effect, while the rest of the climate change effect was due to warming during 2022. Now, it's worth highlighting that all of these results I have shown or I have mentioned without figures are actually could be derived through simulation via the MHA methodological model, but also be confirmed through simulation with CLM land surface model. Also, this 30% number you see here. The only difference we found when we checked simulation in this other model is that this lagged effect goes from 40% to 15%. So I wanted to highlight this aspect. I mean, the effect is still large. 15% is quite large, but there is, as you can see, a large uncertainty in this effect, and this highlights the relevance of better understanding this uncertainty, also because they may impact future projections in principle. With that, I'm moving to the topic of spatially compounding fire danger in Europe, which I have introduced already when talking about the 2025 event. And based on that introduction, we can say that when large parts of Europe face fire-conducive weather on the same day, there is potential for widespread fires that could overwhelm the shared EU firefighting resources. And this is why, to look at this type of spatially compounding fire danger, we define the following metric, which is the fraction of the European area under fire weather extreme, so fire weather index above 50. Before doing some analysis with this metric, we checked that actually this metric can give us some insight on wildfires themselves at a continental scale. And this is shown here. Basically, we found that the higher is the value of our metric, so the higher the fraction of EU under fire weather index extreme condition, the larger will be the probability of extreme wildfires at a continental scale. This is shown here by the PDF that transition for the burnt area that transition from towards the right when conditioning on days that have a larger fraction of the European domain under extreme fire weather index. As a first analysis based on this metric, we looked at the cross-country correlations in fire weather index and how they affect the system, let's say. And we found that cross-country correlation in fire weather index increased the likelihood of days where a large fraction of the European Union is simultaneously affected by extreme fire weather. To do that, we first looked at the distribution of our metric, so the fraction of the EU area under fire weather index extreme in green here, and then the same distribution after shuffling basically the countries so that we could break the special the cross-country correlation, and we could get a very different PDF. There is especially in detail, a quite substantial divergence, highlighting therefore that this cross-country correlation enhance the likelihood of days with a large parts of Europe under extreme conditions. The implication of this is that this correlation may challenge the European the EU mechanism, as basically the implication of this result is that multiple countries tend to experience extreme fire weather index on the same day, basically. With this metric, we could also look at the time evolution of the metric itself. And in this case, we looked at the annual maxima of the metric. So the annual maxima of the European land under fire weather index above 50. And this is what we got. So you get not a simple increase towards higher value as one may have expected just based on temperature. And this is very, very well in line with the fact that the fire weather index is driven not only by temperature, but also by relative humidity, precipitation, and wind. We did here run some factorial simulations so as to disentangle the contribution of long-term trends in the individual variables to this overall behavior we see in this figure. And this is what we got. What we learn here is that it's mainly relative humidity in purple and the temperature in red that modulated the overall evolution over time of the metric itself. Something we also wanted to highlight here in view of previous literature is that temperature does not only affect fire weather index in a direct way, simply because it's an input variable in the index, but also indirected because it can modify relative humidity. For example, higher temperature can increase the moisture holding capacity of the atmosphere, and provided that specific humidity doesn't increase, let's say, a lot, this can lead to a decrease in relative humidity. And in this figure here, we are showing this double effect from temperature that I just mentioned by basically changing temperature, but keeping specific humidity to constant condition. In practice, what happened in Europe is that large parts of this reduction in relative humidity was due indeed to higher temperature, and specific humidity increased, but not as much to compensate the increase from saturation of specific humidity. Worth also to saying that these trends you see here, of course, are not just human-induced climate change trends, because large parts of the observed trends, as we know, can be driven just by internal climate variability. So what we did here is to also, although I'm not showing here, to combine the observation with climate model simulation. And what we could conclude is that in the last decade, human-induced climate change contributed to the annual maximum extent of European land under fire weather index extreme by about 15%. And this was largely due, again, due to warming and a decrease in relative humidity. I'm moving now to a quite different topic, let's say beyond simply the weather itself, and we look at compounding effects in the renewable electricity system. So when you think about this system, you can think of, let's say, bad events as those events that happen when there is a high demand for electricity and a low generation. So when we are in this bottom corner here, we characterize these events by looking at extreme values of the residual load, which is the difference between the demand and the generation from wind, solar, and runoff river. So basically renewable electricity generation. And yeah, it's important to say that, and we call these events as renewable electricity drought, which is the acronym here. And it's worth to saying that whether you have these events or not depends on many effects, but of course, largely also on weather. For example, if you have a cold and low wind condition at the same time, you tend to be in this situation in a location where wind dominates the generation, because cold leads to high demand in winter, and winter is the season we are focusing on because of the fact that there is demand for heating. And if there is a low wind, there is little generation. So as a first step here, what we did is to try to understand which are those countries where provided current generation installation capacities. These compounding effects are relevant. So where more than one drivers across all of those you see here is key to describe the anomaly in the residual load during extreme events, during RED, basically. And this is what we found here. So the countries in dark are countries where a large fraction of the renewable electricity drought are affected by multiple drivers, as shown in the map. So there are compounding effects in several regions here, as you can see. And now, as a next step, provided that there is this picture that is sort of quite complicated in the sense there are multiple drivers, we looked at whether there are trends in the frequency of RED events. And that's what we found. We are focusing on winter here, and it's also worth saying that all of this is based on simulations based on the EuroPIPSA framework, which is driven by ERA5 analysis data, under, as a choice, fixed capacities as in the present day. So that basically when we look at trends, this is only driven by trends in weather rather than changes in installation of, for example, new renewable turbine and so on. And well, there is a reduction in the frequency of these events, as you can see here on this map. And the question was now, okay, what's driving this reduction? And we try to get an understanding about that by looking indeed at the contribution to these changes due from the demand, wind, solar, and the correlation between all of these variables. The effect of runoff river is very small, so I'm not showing it here. And yeah, as a key message here, which is quite intuitive, is that demand is what drove this reduction in these events in winter, because of the fact that the warming lowered winter heating demand, therefore this reduced the occurrence of these extreme events. At the same time, we also found a quite interesting effect here from changes in correlation. We couldn't expect it very much in detail, so I'm not also claiming this is, of course, related to human-induced climate change, might well be internal variability. But yeah, correlation between the variables changed, and this contributed to an increase in the events. And this is mainly related to a decrease in the correlation between demand and wind generation, as we could see from other analysis. And yeah, I welcome you to also see further the work from Meng, which also explored also compounding effects, for example, across space, not just across variable in a given region. This leads me to the second last topic, and this is about global breadbasket droughts, soil moisture droughts in particular. And these are type of events that I have introduced. It is a type of event or compound events that I have introduced earlier on. As we said, when you look at the global mice breadbasket, and you think of a situation with a dry condition across the multiple breadbasket, well, this can favor a reduction in crop production across the regions, and therefore this can favor to a reduction in the aggregated global scale production, which can have repercussions. So here, to monitor this type of compound events, we looked as a metric here, we looked at a fraction of the global breadbasket area under drought, soil moisture drought. And to advance further here the field, we looked at record-shattering events into these compound events. And these record-shattering events are events that mark a step change beyond past experience, which may challenge adaptation capacity. And they've been pushed forward more and more in the literature, for example, largely by Eric Fisher and also Vic Thompson, among others. How can we visualize these events to better understand what they are? Well, this is the metric we are looking at, so the fraction of the global breadbasket under drought. And you can see here the evolution over time of this metric. In blue, it's shown what are record-breaking events, so events that have no value larger than them at the time of their occurrence. And then there is only one in this case. There is here a record-shattering events, which is not only a record-breaking, but is more than that because it exceeds any previous record by large margin. In this case, by at least 5% in our analysis. And what we did here is to check what's the probability of having these record-shattering events in the remaining part of the century, so from now until the end of the century. And that's the result we got. In red, basically, we can see that the probability of having at least one global record-shattering event by the end of the century is around 50%, 52% in this case. There is also a range here, which is the range across the multiple smiles that we could analyze. And this is a result under SSP 4.5, so a scenario in terms of greenhouse gas emission that is intermediate. So it's not extreme, it's in line with current policies, but still you see that this this probability is quite high. And is much higher, in particular, that's key, than what you get if you detrended the trend all the soil moisture across all grid points in the breadbasket region. So it means it's 7 times higher than that. So it means that there are some trends in soil moisture across breadbasket region that somehow favor these elevated probabilities here in red. We could ask which regions are subjected to a trend, so to a drying trend in soil moisture that lead to these elevated probabilities. And our reply is that Brazil, Europe, and US are those regions which are going to experience, according to this model, a strong drying and therefore favor these elevated probabilities. Another question we asked here is which are the regions that experience a regional record-shattering event during a global scale record-shattering event? And the answer is almost no regions, in the sense that in around 73, in this case, percent of the global scale record-shattering events, there is no region under regional record-shattering events. In the remaining, there is only one region that has a regional record-shattering condition. But what you learn here is that global record-shattering droughts do not emerge from simultaneous regional record-shattering events. Actually, what we find, I'm not showing it here to avoid adding too many plots, is that these global record-shattering events always occur when 2 to 5 regions simultaneously face moderately extreme regional droughts relative to what is the new climate. So on one end, you could argue this is a good result, maybe because of the fact that when we will face these global scale record-shattering events, or at least if we will face these global record-shattering events, they should occur while not all regions are under record-shattering conditions. So this might be easier, hopefully, to handle, although it also highlights some challenges from moderately extreme conditions across regions that altogether may lead to something very extreme at the global scales. And this is something that should be explored further by connecting this drought condition with crop models, for example. So before concluding, I have a final slide on a topic that is, I would say, I would imagine of broad interest. And this relates to the calendar year of 2024, which, as we know, was the first calendar year that exceeded 1.5 degree of global warming. We had 1.55 according to the mean of observational dataset. The question is here, what does a year above 1.5 degree mean for long-term warming level targets? Because the implication is not obvious, as we know that because we know that the Paris Agreement 1.5 degree limit is typically measured via temperature averaged over a 20-year period, not just by temperature over a single calendar year, because of course the temperature of a single calendar year can oscillate up and down also because of internal climate variability, while we want to more focus on the human-induced component. And so here we ask the question, what does this single year mean for the long-term warming level target? So in principle, we might be in a situation where the first year at 1.5 shown here might occur well before or before the 20-year period at 1.5. But we might also be in a situation like this, where this year occurs within the window at 1.5. Therefore, such a first year at 1.5 will signal us that we have already entered this 20-year period at 1.5, which has some consequences. So in which pattern are we? This one, so the first one or the second one? We looked at observation first of all, and we found that this second pattern, so the one we see here, is the one that we observed when we reached the most recent cooler warming level, so 0.6, 0.7, and so on. So this is already an indication that this is what we might experience also for 1.5, but of course that's not enough to conclude. And therefore we also looked at climate model simulations, and we checked which pattern to expect. And we looked at different SSP scenario. Now we can focus, for example, on the SSP 2.24.5, which is in line with current policies. And this is the distribution of basically the positioning of the first year at 1.5 relative to this 20-year period. So all models here are place this first year at 1.5 within the window. So basically this says, okay, this is the pattern that models are showing. That's what this plot is telling us. And then, okay, you can see the plots, the results according to more extreme and less extreme emission scenarios. And yeah, only if you look at the stringent or very stringent mitigation pathways, for example, for the SSP 1.9, and also not all models emit the 1.5 degree itself. But in this case, the probability is still quite high. So what does that mean overall? Well, that without stringent climate mitigation, it is highly probable that that we have already entered the 1.5 degree window, so that we are already in a 1.5 degree era, where basically the projected impacts of a 1.5 degree world are expected to emerge. Well, why is that? Because in the past we looked at what could have been the impacts of a 1.5 degree warmer world, and most studies looked at extreme events within a window of 20 years. And well, we are already in that window, basically. So that's the first thing. And yeah, as a third approach to look at this type of question, we looked at some idealized simulation just to get a feeling of, okay, how much should we reduce the temperature trend so as to achieve a probability of only 50% of already being in a 20-year period at 1.5. And well, this achieving a probability of only 50%, which by the way is also quite high, well, it would require an immediate reduction of temperature trends to 20% of today's rate. And that's obviously, unfortunately, a very strong reduction. Yeah, so not happiest slide, let's say. But of course, yeah, we should do our best to limit global warming, as we know, to the minimum possible level. And also, if reaching 1.5, eventually to overshoot, go down that road. And yeah, concluding, we've seen that compound events can cause many high impact events. Therefore, a compound event perspective on climate hazard is helpful because it can support with more impact related assessment. Compound event lenses can naturally help to disentangle the contribution of the different drivers to these high impact events, therefore helping with process understanding. And studying compound events requires a large sample size. We should be aware of that when looking at observation. When looking at models, SMILES can be of help. And also at the same time, the storyline approach, which we have seen, for example, for the drought, but we are also using in other studies recently, for example, with nudged climate model simulations. Well, it's very well suited for very rare and complex events. Therefore, it's perfect for studying compound events and then better understanding them. As we approach the 1.5 limit of the Paris Agreement, we should be aware that high impact events may change through changes in multiple underlying drivers of the events and they interplay as well. And with that, I thank you very much for your attention, and I'm happy to chat more with you about this.